Hello, it is my pleasure to speak at the Advantech IoT Virtual Summit about machine vision technologies and their applications in Industry 4.0. Let me begin by saying a few words about the company. Advantech is the largest company worldwide with an exclusive focus on developing and advancing machine vision software technologies and algorithms and packaging those into standard products. We are a privately held company with headquarters in Munich, Germany, and currently have about 200 employees worldwide. I'm personally responsible for Advantech's branch office in Boston, Massachusetts, serving the North American market. A quick glance at our product portfolio. Like I said, Advantech provides standard machine vision software to users who want to develop and deploy their own machine vision applications. And in addition to that, we provide services assistance. We provide our expertise and competence to help our customers be successful with their machine vision deployments. Let me jump into the subject matter of my talk by asking, why is there so much hype about deep learning? We hear about it almost every day in the news, not just in the context of computer vision or recognizing images, but also in the context of analyzing stock market patterns, health data, and so on and so forth. People almost tend to expect some sort of magic from the technology, and that includes the machine vision market as well, as I realized talking to some members of the community here. But is that hype really justified? Well, let's first take a look at what the typical applications of deep learning in machine vision are. So basically, you can divide them into three main categories, and a lot of other applications can be derived from those. So on one hand, deep learning can be used for image classification, and that could mean, for example, determining whether a part is good or bad in production just from the image itself. Another possible application is to look at object detection. So here we are not just classifying images as a whole, we are also identifying objects within the image, and we can determine their position. Last but not least, deep learning can also be used for image segmentation. A typical example application for that would be if you would like to reject pills based on the size of surface defects. So if you have a criteria, let's say, that says if the defect is more than 5% of the total surface of the pill, you could use deep learning in order to segment the defect and then use traditional blob analysis to determine the size of the blob and then make a pass or fail decision. How does all that magic work? Let's take a look at the training. So in essence, what we have to do as users is we have to provide labeled data. In case of image classification, that means we have to annotate every single image and tell, for example, if what we're seeing is a good or a bad part. Likewise, if you're looking to use deep learning for object detection or semantic segmentation, you also have to provide labeled images, basically giving the information that you eventually expect the deep learning network to determine on its own. Once you provided all that labeled data, and typically you need somewhere between 20, 50 to several hundred images to train a deep neural network. In the training itself, basically the input data, the images with the associated label, is matched to the desired output. And the network is optimized to basically create a statistical model that is supposed to then make decisions just based on plain images autonomously. So once the training is completed, the expectation is all you have to do is feed in an image into the deep neural network, and then the deep neural networks should make the decision for you. In other words, tell you what type of object you're seeing, if it's a pass or a fail, where the objects are located in the image, or where pixel defects are located in the image if you're looking to use it for semantic segmentation. So the question is this really the magic tool that we need for machine vision, and is everything else obsolete? And I would like to answer the question by walking you through a few typical applications and giving you a sense for whether deep learning is useful in each of those cases or maybe not. So let's start with this one here. And a good way, by the way, to determine whether deep learning is the right approach or not is to ask yourself as a human, would you be doing a good job at solving the task? So what does that mean? So if I gave you that diamond and asked you, what is the angle between those edges at the tip? You would probably say, well, it's somewhere between 90 and 135 degrees. However, if I asked you to determine the angle with an accuracy of half a degree, you would probably not do a very good estimate. In other words, if high accuracy is required, most likely deep learning will not be the right approach, and you would be better off using classical machine visions like edge detection and determining the angle based on simple geometric relationships. So let's take a look at another very common technique that is used in machine vision, and that is 2D pattern matching. And 2D pattern matching is the technique, but the application of it is to locate objects in the image and associate that location, for example, to robot coordinates so the object can be grasped by a robot. Now, if you look at those 6 images here, you might notice that what they have in common is that you're always looking at the same object. There are not multiple objects in one image. And for that very reason, traditional 2D pattern matching is a very well-suited approach. Here's how it works. You take an image of the part that you would like to find, and basically the algorithm behind the scenes learns its geometric features, for example, and then that part can be found on a pile of parts, and you get the position and orientation. It is a very simple, straightforward technique, and the reason why it's used so often because besides robotic applications, in most applications, parts are moving, right? And typically that means you have to align regions of interest, such as caliper tools, for example. So pattern matching is probably used, I would say, in maybe half of all machine vision applications, if not more. It's a very robust technique. It works well. It has been around for a long time. It has been improved many times over by different vendors offering that technique. And it's very easy to use. It can be trained or adjusted by engineers in production without knowledge of machine vision, simply by taking a picture of a part and hitting a train button, and everything else pretty much happens behind the scenes. So let's take a look at position detection from a different angle. If you recall a few slides ago, I mentioned that this is also a potential application for deep learning. But what does it mean now? I mean, when would a classical approach be better, and when would a deep learning approach be better? And there is an important difference between classical pattern matching and deep learning-based object detection. And that is, in classical pattern matching, you train one template, and then you search for that same template in the image. You, of course, can also train multiple templates and search for multiple objects at the same time. But in essence, the training and the runtime scales with the number of objects you're trying to locate. So in other words, pattern matching or traditional pattern matching is not a classification tool. And here's the power of where the power of deep learning comes in. Deep learning can not only locate objects, it can also classify them and identify them at the same time. So no matter how many different types of objects you're trying to locate, as long as you have trained them all, you can do that in one approach, basically without any influence on the runtime, for example. And there are also scenarios where traditional 2D pattern matching methods would not fare very well. If you look at the leftmost image here on that slide, for example, you'll notice that you're looking at a can, and you obviously don't know which side of the can is facing the camera. So for that reason, it is very difficult for classical pattern matching algorithms to do a good job here. And in addition, like if you look at the second image, for example, you also have objects that are overlapping by 70–80%. And classical pattern matching methods, they can cope with overlap to some extent, but once it gets, let's say, beyond 50%, they probably also struggle to provide robust results. And again, the third main advantage of using deep learning for position detection is that it can handle multiple objects at the same time. So it can identify objects in the image and also locate them. Now you might wonder, what is the downside? Well, the downside is, like I mentioned earlier, for deep learning, you always need not just one single image, but you need probably several 10 or maybe 100 images for training. Often you don't have these images, especially if you want to retrain quickly on the fly in production, then it would not be a very convenient approach. And another downside of deep learning is the accuracy. Generally, if you're using traditional pattern matching, you get a better accuracy in regards to the position orientation of the part than you would be able to achieve with deep learning. So let's take a look at another very common area in 2D machine vision, and that is code reading. So code reading is used across, pretty much all industries. Whenever you're producing parts, they always have to be tracked in the factory, right? You want to know where your parts are at one point. And obviously, the logistics industry has just been booming lately due to the rise of e-commerce. And that poses particular challenges to code reading applications, because often we have to look at labels that are wrinkled, we have to look at labels that are partially torn, or labels that are hidden behind a plastic wrap. So it can be quite challenging. And this is also an area where deep learning and traditional methods meet. So code reading applications are well suited for deep learning in the sense that deep learning would be able to locate these codes in the image. On the other hand, for some applications like 1D barcode reading, you still have to determine the width of the bars and the gaps in between the bars. And for that particular step, classical machine vision or metrology tools are still in use today. But frankly, all those are implementation details. So all you care about as a user is really, does the tool read the code reliably? And you don't care so much about the application. So let's talk a little bit about 3D position recognition. Now, 3D position recognition and 2D position recognition are very much related, especially except that you have an additional degree of freedom, and possibly you might be looking at a 3D point cloud instead of just a 2D image. So what is the better approach here? Deep learning or traditional pattern matching methods? And again, like before, it comes down to the requirements of the application. So ask yourself again, if I gave you a picture, or if I asked you to look at a pile of object, and I asked you to give me the roll, pitch, and yaw value of the topmost object, you probably would be way off. So that means likely deep learning is not a very good solution here, and you're better off using classical pattern matching methods that can cope with 3 or 6 degrees of freedom. Now, if, on the other hand, I asked you to simply grasp one of these objects from that pile and put it into a different bin, then obviously this would be a piece of cake. So for this particular application, deep learning might be well suited. So for position recognition applications, you have to look at the requirements in a little bit more detail. And I would like to show you an example application that was solved with classical machine vision pattern matching that operates on 3D surfaces. This is a robot cell that was developed by one of our partner companies, an integrator located in Lexington, Kentucky, called Kinemetrics. And they have designed a robot cells that basically feeds parts from a bin into a conveyor, picks them up from a conveyor with the robot, and as you can see in the lower left image here, puts that part into a fixture so that orange clip can be inserted into the part. Now, in this application, the parts on the conveyor are coming in at random. So it was necessary to determine all 6 degrees of freedom here, so the robot can basically come and grasp that part at the right position. And since we have to place that part very accurately, this really was not an application that would be suitable for deep learning, but rather using classical, I shouldn't say classical, but basically pattern matching that looks at 3D surface features. Now let's move on to a typical deep learning application. So let's say you're looking at inspecting class for quality, and in particular, you would like to classify defects within that class and to make basically derive some knowledge about what goes wrong in the production process. Now, if someone is trained at what types of defects we need to find and how these look like, again, a human would probably do a pretty good job. And if you ask that human to translate what he knows about glass into machine vision language or features or a sequence of commands and operations, then he probably would have a hard time to do that. And that is a good indication that this is an application well suited for deep learning. And by the way, this is also a classification application, of course, which is one of the core methods of deep learning, as I showed you earlier. Here's another application where the task was to identify, or actually to tell whether a slot on the shelf in a warehouse is full or empty. And the reason why that was of interest is that you basically have an automated forklift that is driving through the aisles here, and that forklift is supposed to restock the shelf. And before putting new items onto the shelf, of course, it better make sure that there's nothing on the shelf yet. So the simple task was here to determine whether a slot was empty or occupied. And it seemed like an easy application at first glance. However, what made that somewhat challenging is that you're looking at an uncontrolled environment, right? Lighting is difficult to control in that warehouse. And besides that, quite often you're looking through the shelf and you might be seeing other items on the other side of the shelf, or even another forklift that's driving through the next aisle. And for that very reason, you have conditions are very hard to control here. Deep learning actually proved to be a very reliable technology here. In fact, this particular application was initially solved with traditional machine vision methods using a 3D sensor. And obviously, if you have depth information, you can gain much more from that than if you're simply looking at a 2D image, right? The downside was that 3D sensors are also a little bit pricey. So what they tried is they tried to solve this with simply a 2D sensor, a standard camera, and replacing a traditional rule-based approach with a deep learning-based approach. And not only did they end up saving cost, they also were able to make the application more reliable and more robust. So looking at those few examples, you might ask yourself, well, is deep learning the holy grail of machine vision, yes or no? And I think you probably can guess what my recommendation or take on that is. Deep learning certainly is a very powerful technology, but it also has its downsides. So what about the upsides? As we have seen, deep learning can solve some really tough applications that are hard to tackle with classical machine vision methods. Deep learning can possibly shorten the development time because it doesn't require any sort of rule-based programming. And it also requires fewer experts. Anyone can label images. Coming up with a set of rules or an algorithm that solves a machine vision application is, in some cases, you need a machine vision expert for that. And they're not that easy to find. Now, what about the cons? One con I already mentioned earlier, deep learning does require a significant amount of data for training, and those data are not always available in production. Especially if you think about starting a new production run, for example, and producing a part that you've never produced before, it is typically hard to come up with defects. And for that very reason, it might be very difficult to come up with a large enough training set. Also, a common complaint that I hear from customers, and I believe rightfully so, is that deep learning is a black box. Once a deep learning network is trained, there's little you can adjust, right? The only way you can change its behavior is to retrain it using a different image set. What people in production are looking for, however, is to have a few knobs that allow them to change a bias or so, or change a parameter to pass or to fail more parts. And that, unfortunately, is not easily accessible with deep learning. So the way we look at it at MVTec is really deep learning is not the holy grail. It's not the magic tool that will solve every application. It's another tool in your machine vision toolbox, and it really comes down to selecting the right tool for the task. So my general advice is don't get hung up on a specific technology. Really try to determine what is best suited for the particular application you're trying to solve. And that's where we at MVTec can help you. So you got my contact information here. If you would like to contact me personally and talk about one of your applications, I'll be happy to talk to you about it and offer you my personal recommendations. So thank you very much for listening and enjoy the rest of the summit.